So it's CCC and then O. Okay. I'll let you look at it for a second, and I'm going to put it on the board. CCC and O. Okay. C, oh, right. C, 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 and was it a double bonded O? I think it was. Yep, double bonded O. Okay. All right. Okay. Sometimes they're going to give you, like, they won't even give you this much information. They'll give you a picture of a molecule. And from the picture, you're supposed to know, without ever having been taught, what color means what atom. So that's a little hard, you know. It's like me saying, guess what my aunt's name is. If you can guess it, you get 100 on the exam. You know, that's insane. So they really need to teach it before they ask about it. So that's one of the things that I put on the document that I'm going to put on there for the homework is like what color represents what atom. Yeah, carbon is gray, hydrogen's white, the halogens are green, nitrogen is blue, and oxygen is red, and stuff like that. Yeah, it's red. And, okay, all right, so if you look at something like this, the first thing you'll notice is that not all of the carbons have hydrogen, right? So you have to add in the hydrogen. Sometimes you just expect that you know that, but you might not know that. Most of the time, if you see something like this where they've left out the hydrogen, they don't want you to just automatically start throwing in a bunch of double bonds everywhere. Occasionally, you have to do something like that, but you can tell whether or not you have to do it. A lot of times you click on the hint and it says, or you read the question, it says, be careful of formal charges. That means there's going to be a weird double bond somewhere. And usually, like the one that they had on your homework had a sulfur in it, and the sulfur ends up going past an octet when you have it with the lowest formal charge. Mm-hmm. And so, you know, if they're asking about decreasing your formal charges, then you're going to have to choose between a couple structures. So, but that's not too terrible. So anyway, so now we've got all the carbons here, and you can ask a lot of different questions. Well, you can ask 3 questions about this. You can say things like, what is the geometry around, and then they'll name something. Or what is the hybridization on the, and they'll give you something. And then the other one is, what's the angle around that particular atom? So we will label these. If they said in this case, they couldn't say the central carbon because there's more than 3. But if they only have 3 carbons, the central carbon would be the one on the inside, even though normally when we talk about a central atom, we're just talking about something surrounded by other stuff. And all of the carbons in a 3-carbon chain, it's going to have like hydrogens and things on it. So, okay, that's a good question. Because the carbon has to make 4 bonds, and nitrogen has a tendency to sometimes, well, actually I didn't add enough, to sometimes like keep its lone pair, and it'll have, you know, 2 hydrogen. The main thing is trying to keep everything with an octet. So that's the main thing here. Just to make sure everything has an octet. And if they don't have an octet, and you're like, I think this needs more atoms, the only atom they'll leave off is hydrogen. So you don't have to guess, like, do they mean I should put a fluorine here? Because if they leave it off, the only one they ever leave off is hydrogen. Unless they've made a typing error, in which case they messed it up. You're welcome. Another thing that can help you on your homework, if you get, like, try to do it on your own, but if you get completely stumped, you can go to Google and type in Lewis structure of, and then either put in the formula or put in the name of it or whatever. It pops right up. So the reason I don't want you to do that first is because when you get to the test and you have to do it without Google, then even though you kind of know how to do it, it'll make it a little harder to do. Yes, yes. Yeah, they should give you the information. And I was doing stuff like I was clicking on their hints, which are almost useless. And then the one that asked about chiral compound sent me to a page that had nothing on it about chirality. Nothing. Chirality is in section 5.6. So, I don't know who came up with this brilliant book, but alrighty. But yeah, they don't. All right. So I just labeled them alpha, beta, gamma. Oh, cool. Okay. Sandra's got a poll there for you guys to vote on. All right. So with this, the first thing I'm going to show you how to do is geometry. So we're going to start with the alpha carbon here. And with the alpha carbon, I'm going to consider the carbon here is my central atom. And then the things that I'm going to look at to figure out my steric number. Steric number is number of lone pairs on the central atom plus number of atoms bonded to it. So the steric number for the alpha carbon is 4. And the reason is because you have hydrogen is 1, this is a second one, that's a third one, and this carbon here is a fourth one. Even though the carbon leads to all this other stuff, it doesn't matter. You're just going to look at the thing that's directly attached to it, not the stuff that's attached to the stuff that's attached to it, if that makes sense. So the steric number would be 4. It has, so anything with a steric number of 4 is what shape? Like the electron geometry. What's the electron geometry? Tetrahedral. All right, you guys got it. All right, so that's tetrahedral. So that's the electron geometry. What is the molecular geometry? It's going to be the same, right? And we know it's going to be the same because there are no lone pairs on the carbon. So if it's tetrahedral, what's the angle? (109.5). And then we're going to figure out the hybridization. Let's switch to orange. And remember, it's the one where you go S, P, D, F. You can go up to 3 P's and 5 D's and 7 F's. So we're going to go around. And so this is, we'll call this atom S. Let me say P. That's P1. P2. And P3. So that would be SP3. One of the things that I noticed when you put in SP3 into the program, you can't put in capital S and capital P. You have to put in lowercase s and lowercase p, otherwise it marks you wrong. So if you put in the right answer and it marks you wrong, check to make sure you don't have capitals. So let's say there's one question, it's like carbon, it's got some hydrogens attached to it. And they ask you to look at the central carbon. So the central carbon that they are talking about is the one in the middle. In this case, it'd be hard to say the central carbon because there are 4 things. There's carbon, 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 and nitrogen. So they would be talking about central of those. You can't really go in the middle of that because there are 2 on each side. They would be equally split. So they would have to label them like carbon 1 or carbon 2 or give them a little star and say, you know, looking at the carbon that's indicated in the picture or something like that. Yes, absolutely, it is. It's based on the number of bonds that the atom makes. You want to remember to include the lone pairs as well. And okay, so we're going to do the next one. So let's take a look at beta carbon. Looking at the beta carbon, see if you can do that one on your own. What is it? Actually, that's what we're going to do right now, Chad. That's a really good way to lead into it. All right, so what is the geometry of the beta carbon? So that's the carbon with the little B shape next to it that I wrote in. So how many atoms is that carbon bonded to? Trigonal planar. Perfect. Yes. It's 3. So it's bonded to 3 things. It's bonded to this carbon here. It's bonded to this oxygen. And it's bonded to this carbon. So it's got 3 things. It's got no lone pairs. So it's going to be trigonal planar for electron geometry and molecular geometry. All right. And then Chad was asking about sp2 geometry and how do you know it's sp2? And it's the same thing. You're just going to count electron areas as you go around. I say electron areas because I'm not going to say bonds, because if you look at the oxygen, there's a double bond there. And some people might say, well, that looks like 2 bonds. And other people might say it's 1 double bond, so then they might call it 1. So I just say electron areas. Also, that would include a lone pair. So here's 1 electron area. Here's a second one, and a third one. So we've got S, P1, P2, so that's 3, and you're finished at that point. So this one is going to be SP2. Oh, okay, you're talking about the lone pairs on the oxygen? Is that what you mean, Sierra? Yes, okay, that's a good question. Because when we're looking for the hybridization, the only ones that hybridize that we're going to be working with are the ones that are in the middle that have a bunch of stuff connected to it. And oxygen, there's only one thing connected to it, and that's carbon. There's nothing else, so it's considered terminal. And being terminal is not going to have hybrid orbitals. So if it's terminal, like on the end, which would be all of the hydrogens plus that oxygen are all terminal. And so they're not going to hybridize. Only the central atoms will have hybrid orbitals. So we're only concerned with what's directly connected to the carbon itself. And it doesn't matter that oxygen has lone pairs. It wouldn't matter if carbon had lone pairs, but not so much oxygen. Exactly, Chad. That's exactly how you do that. Absolutely. Okay. So I'm going to do it in black. So we're counting the things that are directly connected to the carbon. So 1, 2, 3. There are 3 things. So I'm going to go S, P1, P2. So that's 1, 2, 3 of them. And then my answer is just going to be SP2. So you say it P1, P2, P3 because it, hang on one second, my iPad wants to die now. Come on. Alrighty. Okay, that's better. Just so you can keep a count of how many you have. Let's see. SP always 1 less than the steric number. Well, when you're talking about the P's, but if you get something that goes past P, so if you had something that had 4 things attached to it, you would say S, P1, P2, P3, and then you have to go to D after that. So that would be SP3D1 or SP3D. I mean, that would mean the same thing. And then how would you do this on skeletal structures that don't show the carbons or the hydrogens? Okay, I'll show you that in just a second. Let's do the nitrogen because the nitrogen has lone pair. So the nitrogen has how many bonds? Not how many bonds. How many atoms are attached to nitrogen? 3, correct? So there's the carbon, this hydrogen, and this hydrogen. And how many lone pairs?
2 or 1.
1. So the steric number is always the atoms bonded, so we said that was 3, plus the number of lone pairs on the atom that we're looking at, so that's 1. So the steric number is 4. If the steric number is 4, we determined before that when the steric number is 4, the electron geometry is tetrahedral. So this is for that nitrogen. However, the molecular geometry was also tetrahedral before because we had no lone pair. Now we have 1 lone pair. So we would have had something that looked like this. But now, instead, we just have the bottom part because the other piece is a lone pair. What do we call, oh, you guys are faster than me. And so that would be trigonal pyramidal. So what's the hybridization on that? And is sp2. Perfect. All right. Pick green. All right. So that would be, we're looking at this H. Actually, it would be more than that. The sp3. But let me show you why. So we're looking at all of the atoms that are bonded to it, plus, no, I don't want to update my computer right now. Seriously? No, I'm not doing it. Get over yourself. Quit. It doesn't want to let me do anything now. It's like, update now? And I'm like, no. How do I, oh, I know how to get out of it. 1 second. Quit. You won't quit. Not updating it. Okay. All right, my computer's no longer hijacked by the update. Yeah, so the angle's going to be less than 1 or 9.5. All right. So we're also looking at the lone pair. So I would say S, P1, P2, P3. So the hybridization there would be sp3. Am I doing that right? I think so. Yeah. You ever do something you've done 100 times and then you look at it and you're like, is that right? Kind of like you write a word and then all of a sudden you look at the word and you're like, is it really spelled like that? Yes, the lone pair counts. Yep. All right. Anybody need a second on this page before I talk about how to add in the hydrogen? No, yes? Okay. Just let me know when you finish, Samantha. No, you could have started you could have started counting on any of those, and you could have even not counted on a particular atom and just said there are 3 atoms and 1 lone pair, so that's 4 things. And then on your fingers, you could have said S, P1, P2, P3. So you're not really assigning the S to the lone pair or to the hydrogen. You're just saying, okay, there are 4 things around it. I'm going to count like this: S, P1, P2, P3. You have a question about the other one. What's your question, Chad?
Okay, it's like the carbon-oxygen bond. If you count it like S, P1, P2, and like the lone pairs count, like wouldn't it be S, P1, P2, P3, and then D.
So which one are you looking at? Are you looking at the nitrogen or the carbon with the oxygen?
The carbon with the oxygen.
Okay, all right. So with that, we're counting this carbon here, the oxygen, and then this carbon. And we're looking directly at this carbon to see whether or not it has a lone pair. So that carbon has no lone pair. So that's why we say it has 3 bonds, or 3 things bonded to it, and no lone pairs. And that's why it makes it trigonal planar. And so as you go around it, you'd say I have, 3 things. Let me pick a color you can see. I have 3 things bonded to it, and no lone pairs. So that would be 3 things. That would be S, P1, P2. SP2 would be the answer for that one. Does that make sense? Yeah. Okay. All right. Because it would be tempting to try to add in the lone pair on the oxygen, but the lone pair on the oxygen belong to just the oxygen. They don't have anything to do with the carbon when you're looking at hybridization. All right. So let's say they give you something like that. Yeah, so we're just looking at the central atom. All right. So let's say they give you a shape like this, and they say, okay, put it in the thing and build it. One thing to remember, when you're finished building it, up at the top in the little menu, it has a little thing that looks kind of like this. It's like a little tiny set of axes. You have to click on that, and then it'll make your shape the correct shape. So when you're trying to do it yourself, your bonds may end up being a little long or a little crooked, and then your shape may be a little wonky. But when you hit this button here, it unwonkifies it. Wonkify. That's a new word. That's like something that should be on a t-shirt. So it fixes it, and it makes the angles correct. It's what's called being optimized. So the computer optimizes it by running some mathematical equations, and then sets the angles correct based on a force field, an imaginary force field. Okay, so every time you see a point, that's a carbon. And yeah, I wouldn't have known that except I did some molecular modeling stuff in graduate school. And I was like, there should be a button on here somewhere to fix that, because mine was so weird. All right, so every time you see a point like that one, that was bizarre, then you're going to get, it stands for a carbon. So there are, how many points are there on that ring? 6, right? And they go around kind of in a ring. So it's C, 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 C. This is how I did it in the program. I just put a bunch of C's together, and then you click on one of the carbons and then just drag toward the other carbon, making sure that over on this side, you have like a little thing that looks like this. If you click down in the corner, you can pick either a double bond or a triple bond, but it starts out automatically as a single bond. So you just do it again, and again, and again, and again, and again. There's also a little undo button up there. So if you find that, you've done something like you add an extra carbon or something, you can just hit the undo button. It goes away. All right. So we've got that part. Now, the little circle in the middle has to do with it being, I don't want to say hybridized because we're talking about hybrids in a different way, but it has resonance. And so before we put the resonance in, we want to kind of, resonance meaning it's aromatic resonance. Aromatic means it alternates single bond, double bond, single bond, double bond. So we're going to finish out the rest of the structure first so we don't put the double bonds in the wrong place accidentally. All right, so the rest of the structure has a point here, here, and here. So we're going to add 3 more carbons, carbon, 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 and then connect them. And then now we've got to add in the hydrogen. Before we add in the hydrogen, we're going to go ahead and put in the double bonds in the aromatic piece. So when I do that, I need to be really careful that I don't put them in the wrong place. So let's say if instead of a single bond right here, I had a double bond, that would be like 2, 3, 4, and obviously I don't want to put a double bond on that carbon because then I would be giving it too many electrons. In this case, it's just a single bond, so it doesn't really matter where you put the double bond to start with. So I'm going to put it there. I'm going to skip one, and skip one, and then I'm done. So it's just every other one. When you get every other one like that, it does what's called delocalizing the electrons, and it spreads them out over that whole ring. And that makes it more stable by decreasing the repulsion of the electrons for each other in the ring. Now is when we're going to add in the hydrogen. At this point, we know that whatever doesn't have enough bonds, it has to be filled up with hydrogen. So, for example, this carbon here has 3 bonds, so that would be 2 electrons, 4, 6, and we've got to add the 8th one. We're going to add a hydrogen there. And it's going to be the same for every carbon all the way around in this ring, except probably the last one. All right, now looking at, I'm going to do this with red. Looking at this carbon here, it's 2, 4, 6, 8. So I'm not going to put a hydrogen there. Right? The next carbon here is going to get 2 hydrogen, and this one's going to get 2, and this one on the end is going to get 3, just so that all the carbons have the correct number of electrons around it. And so that's how you would do an aromatic ring structure and then add in the carbons to it. Any questions on that one? Everybody's good there? All right, anybody need a second on this page? How come 2 of the carbons have double bonds? You mean this one, and this one here? The reason that those have double bonds is because when we're looking at the original structure, we saw this circle. And anytime you have a ring structure with a circle, like even if we had a pentagon with a circle in it, that would mean that the pentagon is alternating double bonds. So double bond, single bond, double bond, single bond. In this case, it's a little weird. I think you have to have kind of like an even number. So like octagon or something like that. And then you would just alternate. Every other bond is going to be a double bond. So that's what the circle inside means. All right. I'm going to clear this. And then take a look at 6.1 and see what forces they talked about. All right, and it was, I'll just tell you about all the forces. They're going to ask you about them all anyway. Okay, so there are a couple of different ones. There are London forces. Everything has these. They're temporary dipoles. So for example, you have one atom here, you have one atom here. They both have protons in the middle and electrons on the outside. if you bring those together, this electron and this electron are going to repel. So one of them is going to run around to the other side. So then you're going to have something that looks like this. And then the other one is going to be kind of bare in the front and negative on the back. And so they're temporarily having their electrons in one direction, and that's basically the electrons are in that direction. So that would be a London force. They also are called dispersion forces because the technical name is London dispersion force. And sometimes they're called temporary dipole moments. They're called all of those things, but that's what it's talking about. And you see that the more stackable something is and the larger it is, the more London forces it has. For example, if you have something like this, that's very stackable. It's going to have good London forces. If you have something like this, that's not very stackable, right, between those two molecules. That's not going to work out too well. And then if you were looking at something like this one and then compared it to something like this, the bigger the molecule, the more strongly it's held together because it has more London forces. So if you were going to compare these two, this one has more London forces than the other one. All right, so let's take a look at the next one. And then we have polar molecules can be held together by dipole moments. So, for example, if you have I'm not going to add in all the lone pairs around each fluorine, but they would all look like that one, right? And then I have another one. This is partially positive, and this is partially negative. It would try to somehow orient in such a way that the fluorines are as far away from each other as possible, and that the middle carbon could be as close to the fluorine as you could get it, which would be kind of hard to draw. If one of those, and then you might have like a fluorine from another one kind of pointed in like this, and then that would be being held together by polar forces. Or if you had carbon dioxide, then you would have something like that. So they're going to orient themselves, and that's going to hold them together. All right, now we've got a whole minute left, and I will show you the last one, which is the strongest one. It's hydrogen bonding. And so it's going to be a hydrogen connected to a nitrogen or a halogen, well, not halogen, but a fluorine, or an oxygen. So for example, with water, it'll have hydrogen bonding between one atom and another one. So between these two, it's going to hold those two water molecules together. The stronger the forces are, the more forces there are, the harder it is to separate, to have them change phase. For example, if I'm trying to boil water, I have to break the hydrogen bonds and any London dispersion forces. I have to break all of those in between each molecule so that this molecule can float away because I'm trying to boil it off and I'm turning it into a vapor. All right? So that's all we've got time for today. I'll put a little bit more information in the supplemental lecture that I'm going to post later. And all right, if you need anything, just let me know, okay? You're welcome. Yeah, the adaptives are still due. I'm going to work on the adaptive just to take a look and see, should I change it to, if you attempted it you just get a grade for that, or should I keep grading it based on whether or not you hit mastery? So it is still due Sunday, but start with the regular homework problems, then work on each adaptive that is in the assignment. I don't know if we have one or if we have two, but make sure you work on each one, even if you don't hit mastery on either one. At least try to do that. And there will be bonus points on the last exam, and I'm going to email you this afternoon before I start looking at the adaptives. I'll email you exactly what I want you to do for bonus points. The project is due on Monday. Is that a possibility for you guys, or do you want it due on Wednesday?